Okay, I'll get started. Hi everyone. So today Professor Gauri Joshi is traveling, so I'll be taking this lecture on multitask learning. If you have any question, like feel free to type it in the chat or unmute yourself and ask it. Uh, I'm not sure if I'll be able to monitor the chat regularly, so yeah, it'll be better if you can unmute yourself. Okay, so let's get started. So, bit of an introduction about me. I'm Pranay. I'm a research scientist in Professor Gauri's group here in the EC department at CMU. And in a few months, I'll join IIT Bombay as an assistant professor. It's a university in India. And my research interests are in federated learning, which this course is largely about, as well as stochastic optimization. So you must have seen some analysis of federated learning based on stochastic optimization in this course. I also work in reinforcement learning, and recently I've also started working in differential privacy. So one of the lectures, I think on November 11th, will be on privacy. We'll see privacy, differential privacy there. Just a quick announcement on Friday, November 1st. Uh, Yeji Cho from Google will take a guest lecture and it'll start at 11 a.m. And this lecture will be on Yeji's work on ensemble distillation. Yeji is a graduate from Professor Gauri's group here at CMU. Okay, so let's get started. This will be the outline of the lecture. First, I'll give a very brief overview of what you have already studied in the previous lecture, which was on personalized FL. And I'll use that as the starting point for what we are going to discuss today, which is multitask learning. So I'll give some motivation and some application for multitask learning. Then I'll discuss the two broad ways in which multitask learning happens. So the model parameters, you can do something called a hard parameter sharing, which is you make the difference between shared models and uh, individual models in the architecture itself, or it can be something called soft parameter sharing, where you don't explicitly make the distinction, but you do some changes to the loss function or the training process. Then I'll discuss in some detail the multi-objective optimization perspective for multitask learning. So five is sort of a subset of four, but because this will be a large section, I made it a separate section in itself. And finally, I'll mention some very interesting open questions which are still unsolved in multitask learning. Okay, so let's start with what you must have discussed in the previous lecture. So, in standard federated learning, we usually learn a single global model that captures all the, like, it tries to capture the entire data set across all the clients, right? But it often happens that if the data across clients looks very different, then the global model might not be able to capture all that spectrum of data. Specifically, it might not work very well on the clients which have some small amount of data. The other extreme is that every client learns its own local model using only its local data. So this is the local only approach. This is the other extreme. And the drawback here is that even though the model will be tailored to your own data set, but if your data set is too small, you are not going to do much learning either, right? So when you want to generalize it to unseen data, you might not do as well. And therefore, uh, we had this notion of personalization. It turns out that this same problem of learning a global model, but that might not be very good for some data, or learning very specific models, but that might not be generalizable. This is a widespread phenomenon in machine learning, and this gave rise to this paradigm called multitask learning, where we want to learn multiple tasks at the same time. So let's look at some of the motivation and applications for multitask learning. The most common one is robotics. So because there are robots everywhere nowadays. So, one possibility is that whenever you want your robot to learn a new task, for example, play chess or read some books, you make the robot learn from scratch. So, for every new task, you give it some data and you only want this robot to learn using this data, right? However, if robots are to emulate what humans do in practice, then this is not exactly how humans learn, right? We bring a lot of knowledge from a variety of experiences we have in every new task we are learning. So when a kid learns to read, he is or she is using a lot of skills which they have picked up over the years. So this is what we would want our robots to do as well, that they should be able to efficiently learn related tasks simultaneously. Another application for multitask learning is in domains where you don't have a large amount of data. So even though in the most common success stories of deep learning are where you have a lot of data, but there are a number of applications, for example, medical imaging. So if you have some scans for rare diseases, you cannot just collect more and more samples till you can train your model well. Similarly, if you want to do language translation, but you want to translate from, say, English to a rare language, then or you want to translate vice versa from a rare language to English, there is very little corpus for you to go from. There are other applications of this, like personalized medicine. I've already mentioned robotics. In all these domains, the data is very limited. So you want to bring the expertise you have gained from learning in the past with different data sets to this new smaller data set. And as a philosophy, also in general, to design more efficient learning agents, we want them to be able to bring their knowledge from past the tasks they have learned in the past. So, a little detail about this lecture. This is in no way an exhaustive survey of multitask learning. Multitask learning has been studied very extensively, at least since in the past 25 years or so, even more than that, probably. So we'll just look at some specific ideas from multitask learning. If you are interested in learning more, Chelsea Finn from Stanford has an excellent course on deep multitask and meta learning. I have borrowed some ideas from there. I would encourage you to check it out. For this lecture, I have used these two survey papers. Both of them are quite good. The first one is relatively more recent. This one appeared for the first time in 2017, so it is slightly dated. It doesn't spend too much time on neural networks. So the first one, if you're interested in deep learning and intersection of deep learning and multitask learning, the first one would be better. And I'll also give more references for specific ideas all through the presentation. And then the most important references for this talk, I'll have on the very last slide. And finally, I would encourage you to look up something called the Stein's paradox. So this was a paradox in statistics discovered in the 1950s. And you will very quickly see the connections between what we learn today for multitask learning and what was discovered all those years ago. In this, because this is a course on distributed and federated learning, we'll explore a lot of connections between multitask learning and federated learning, how different ideas from multitask learning have been borrowed in federated learning to achieve slightly different goals. We'll discuss some very old ideas. So by very old, I mean they are from mid 2000s, so about 15 to 20 years old. But we'll see how these ideas are used in quite recent work as well. And at the very end, I'll mention some interesting open problems. So let's start with defining what a task is in the name multitask learning. So this definition is not going to be super formal. You can formalize it more, but I think for the purpose of this lecture, this definition would suffice. So suppose we have some data set D and we have some loss function L. This is sufficient to define a task for us. So what we are interested in is we want to learn some model, some machine learning model, f of x. Here, x are the parameters of this model, and this model would like to minimize this loss function over this data set D. So this comprises one task. And during in this talk, you will we will mostly have k such tasks. So we'll have multiple loss functions, multiple data sets, and there will be k such tasks. And if we want to do multitask learning, meaning we want to learn these multiple k tasks together, then it makes sense only if there is some shared structure between these tasks. And this is really an assumption in multitask learning, a crucial assumption. But often in practice, tasks indeed have some shared structure. And the reason for these are, for example, in robotics, so whatever robot you are training, it has to follow the laws of physics. All the objects around it have to follow the laws of physics. So there is some underlying structure to the world itself, which helps us. So if a robot knows how to lift an object, then it also knows how to lift an object and take it to a different place. So because of the laws of physics, there is some relation among the tasks. For example, if you are interested in performing multiple language processing tasks, even then the rules of grammar apply to all the data. So if you have data from the English language, the rules of grammar would stay the same, whether you are doing text summarization or you are doing sentiment analysis. So in essence, the problem of multitask learning is that we want to learn multiple tasks simultaneously. We want to learn them more quickly, more efficiently, in less time, using fewer samples, compared to if we were learning all of them independently. So suppose you train one model using only data for one task, then you train a second model for the second task, third model for the third task. And in every instance, you are only using the data for that task while training a model for it. Then this is learning those tasks independently. And the purpose of multitask learning is that we want to learn these multiple tasks simultaneously. And it is worth it only if we can achieve some advantage by simultaneous learning. So it can be in terms of the runtime. So we are able to train these models quickly, or we get some efficiency. Uh, Only then multitask learning makes sense. I want to differentiate multitask learning from some of the related paradigms which have come up over the years. I won't discuss them. Uh, in a very nuanced discussion, the boundaries between these paradigms get quite blurred. But for the purpose of this for the purpose of this talk, we'll only look at the most basic definitions of these paradigms and then move on to multitask learning. So there's something called transfer learning. Uh, the difference between multitask learning and transfer learning is that in transfer learning, we have one target task and we use all the knowledge we have gained from all the tasks we learned previously. So these are the source tasks. And we use that knowledge to learn one specific target task. On the other hand, as we discussed, in multitask learning, we learn all the tasks simultaneously, right? Then there is something called meta learning, which I guess you discussed briefly for personalization in the previous lecture. Here, we are given data from multiple tasks, but we are interested in learning a new task. And the underlying assumption is that this new task is somehow related to the previous tasks we had data from. So one way it can be related is that this new task comes from the same distribution of tasks from which you saw the earlier tasks. Right. So this is meta learning. And then there are other paradigms like continual learning. So in continual learning, you continuously have tasks coming in and you want to do well on all these tasks. So you build your knowledge up over time and you want to make sure that for every new task, uh, you use the relevant knowledge you have built up and not this any spurious correlation you might have learned. So these are the different paradigms. Okay, so this was the some motivation and some applications of multitask learning. Next, I'll move on to discussing hard parameter sharing. So if I'll wait 1 minute if there is any question. Please feel free to stop me anytime I don't make sense. How does a new task have same distribution? So this is a good question. Yeah. So in meta learning, what might happen is that you have suppose you have a very basic data set like CIFAR 10 and you trained your model to learn the classification for the 10 different classes and then you get a little more data for the same 10 classes, right? So suppose out of say the 50,000 images, you kept 5,000 images and trained on the remaining. And then you want to learn on these additional you want to see how your learned model does on these additional 5,000 images. So this assumption about task distribution, this is not really a strict statistical assumption. So like this is sort of a hand wavy assumption. It might happen that you don't have data from the exact same data set, but you have data from a related data set. So for example, you trained your model on ImageNet dataset or CFAR 100 dataset, and then you want to test it on, say, a smaller dataset like MNIST or CFAR 10 or Fashion MNIST. This would come under the category of that the new task has the same distribution as the original task. So it might be new samples from the same class, but it cannot be entirely new classes which you have never seen. That would be out of distribution. Okay. If there are no more questions, yeah, feel free to write it in chat or unmute yourself. I'll continue. Meta learning can't learn new classes. So there are nuances built on top of meta learning which can do that, but in its very basic construction, it cannot. So as I said, all these categories, all these paradigms have a lot of overlap. So you can like add bells and whistles to the basic meta learning framework, which can give you new capabilities. But in its very basic framework, the new task distribution has to come from the same class of distributions as your original tasks. Yeah. Okay. Okay. Thanks. Okay. So let's discuss something called hard parameter sharing. So the architectures for multitask learning is a more broader category than hard parameter sharing. So hard parameter sharing was an initial suggestion, and then people generalized it in a lot of ways. So what are the factors to consider when you design a multitask learning architecture? So we need to consider so given your model, which of the model parameters you want to share between tasks. Recall there has to be some relation between tasks. So we want to share some parameters which capture that structure. So we have to decide what portion of the parameters to share. We also need to decide how do we design these parameters and how do we combine the shared model, which is common across all tasks, and the task specific parameters, which are unique to the different task models. There is also a balancing game going on when you share some parameters and keep some parameters specific. And the reason is that suppose you share all the parameters, like the all the parameters of the model are common for all the tasks. In that case, we can face something called negative transfer. What it means is that when you try to do well on some tasks, so when the model tries to do well on some tasks, it might end up hurting another task, right? And there can be this trade-off between doing well across tasks. At the other extreme, if we share too little, then we might not be able to capture whatever the shared structure across tasks is, and we might end up overfitting to individual tasks, right? So this balancing between too much sharing and too little sharing, this is more of an art than a science, and like people play around this quite a bit. So let's look at the simplest architecture which people proposed first for multitask learning. So as you can see, this paper is from 1997, more than 25 years back. And this is called a shared bottom or a shared trunk architecture. So I'll explain this if it's not clear in a second. So here we have an input layer from which you can get some features or you can get the training data. So training data comes in from the input layer, and this is the data from all across all the tasks, right? And then we have an output layer. So in the output layer, we have several units, and one unit corresponds to one task. So here this should be K, but we have one unit for every task. If you remember a simple feed forward neural network, you are doing a regression task, you have a single output, right? Here we have k outputs because we have one for every task. And then we have one hidden layer, and this hidden layer is supposed to learn some common feature representation. So if you focus on this part of the network, this is shared between all the so actually I should be a bit more careful with this because yeah, this is the shared part, and then the remaining is task specific. Sorry about my bad handwriting. So for example, this connection and this connection, these are specific to task one, and similarly for the other tasks, right? So you have the initial layer or the initial few layers of the model are shared across all the tasks, and the final layer or the final few layers of the model are specific to different tasks. So if you sort of rotate this thing by 90-degree, you will see the shared parameters at the bottom and the task specific parameters at the top. That's why it's called a shared bottom or a shared trunk model. So this is the same idea in a slightly more general sense. So here now you have multiple shared layers which are shared across all the tasks. And similarly, we have multiple task layers which are specific to the tasks. And so as I said earlier, the shared layers which are shared across tasks, they are supposed to learn the common features across all the tasks. And then you have the output branch, which is specific to each task. And this architecture is very common in computer vision. So this was used in this 2014 paper. So already we are looking at something from 10 years back. And this paper used this architecture for something called facial landmark detection. So facial landmark detection means you want to identify some landmarks on the picture of a face. For example, you might want to identify where the eyes are, where the nose is, where the mouth is, and so on. And this paper realized that instead of training your model to do just facial landmark detection, if you, in addition, also try to learn for a few additional tasks. So, for example, if you try to learn your model to also do head pose estimation and facial attribute inference. So, I'll explain these terms in a second. So, if instead of just training your model to do this one task of landmark detection, if you instead do multitask learning, so to speak, then you get a much better performance. And as we had in the schematic diagram earlier, now again we have input which is going into some shared layers, and eventually we have some task specific layers. So here the first at the top you see the layer for facial landmark detection, and then remaining are the other tasks. So these are some results they have in the paper. So these two are the were the state of the art methods they compared against, and this is TC-TCN is the method they proposed. And as you can see, compared to the first two rows, the third row does much better at identifying these facial landmarks. So here, as you can see, this specific eye is not identified very well. Yeah, and so on. And the two remaining tasks which we discussed, which was the head pose estimation. So head pose estimation means looking at the image, can you identify what is the pose? So is it right profile? Is it a frontal image? And so on. And then the other thing was facial attribute inference. So facial attributes might include, is the person wearing glasses in the image? Is the person smiling? And so on. So when you train your model to do all these tasks simultaneously, it ends up doing well or better than if you were just learning for a single task.
Can I ask a question?
Yeah.
So, can you explain like some intuition, I guess, of like why learning if we're learning more tasks at once, then why it performs better at just doing facial landmarking
Right.
specifically?
Yeah. So let me uh, first say that this is going to be a hand wavy argument. And as I'll mention at the very end, this phenomena that when does this positive transfer across tasks happen and when it does not happen, this is not understood very well mathematically. So the idea is that when you try to learn for multiple tasks, you sort of learn some underlying information about how faces are constructed. Or in general, when you try to learn multiple tasks at the same time, for example, in reinforcement learning or in robotics, you learn some hidden information or some underlying structure about the world itself. Rather than when you are trying to do one specific thing, then it is very likely that if you have a powerful enough model, it will very quickly overfit to whatever your training data is. Does that make sense?
Yeah, it does make sense. And I guess also these other tasks are probably also kind of carefully chosen, like smiling to try and detect
Right,
smiling also probably means that the model is picking up on things to do with the mouth or something like that, which can help with
right,
facial. Okay.
right.
Yeah,
Yeah,
that makes sense.
that's true. Thanks. Okay, so now we looked at a paper from like 10 years back, and okay, it had some architecture and it did some computer vision tasks. What is the relation? Is there anything we can, any insight we can borrow for federated learning? It turns out we can. So this paper from ICML a few years back, and they proposed a method called FedRep. Here, rep stands for representation, and they utilized a very similar idea. So what they did was they assumed that when we train the model across clients, then okay, this might be confusing. So these are the initial layers of the network, and these are the final layers. So they have inverted it in some way. So the idea they came up with was that all the clients will learn will share the initial few layers of their model, but the final layer or the classification layer would be specific to each client, right? So you have shared representation layers and you have local heads or local classifier heads. And what this helped in doing was that the clients were able to learn a shared data representation, right? And as you can see, this is exactly the shared trunk architecture we just saw, and it had some benefits. So yeah, so they learn personalized classifiers. And the benefits were the following. So you can look at the two extremes. One is Fed average, in which all the parameters are shared across all the clients. And the other extreme is local only, where all the parameters are specific to the client itself, right? In local only, so here we are plotting the error versus the number of samples each user has, right? Now it turns out that if you do local only learning and every client only has a few samples, then you are not getting any knowledge transfer from anyone else because you are not talking to each other, right? On the other hand, if you have enough samples, but your model is not too powerful, in that case, you are looking at a lot of data, but because everything is shared, so you are like you are observing something like negative transfer, that you don't have any personalization across clients, right? So a lot of details are just ignored or they cannot be captured. On the other hand, if you share some parameters and keep some parameters specific to the clients, then you can do well across all the regimes, right? And it ends up outperforming Fed average even if you have fewer data samples at every client, right? So this was the shared trunk architecture adapted to the federated setting. And you can think of in this setting, this we are interpreting individual clients as individual tasks. So in a lot of discussion today, we'll see that there is this correspondence between clients and tasks. So whenever I'll talk about extension to the federated setting or uh, any federated implementation of a multitask learning idea, we'll see this correspondence that the clients would be interpreted as tasks. At the very end, I'll talk about something in which is more general than this. Yeah, but for now, tasks means clients. Okay, so let's look at another suggestion. So earlier we had a bottom few layers were shared and the top layers were specific to the task. What if we want to do something a bit more clever? So we have, instead of a single shared bottom layers, we have multiple shared trunks. So this is one trunk, this is another trunk, and all of these are shared across tasks, right? And then at the top, you have task specific layers. So this is clearly more general than what we just saw. What is the benefit and like what are we getting out of this more general architecture? So it turns out now you can, when you are when these task specific layers are getting the input from the previous layers, each task specific output head receives a linear combination of outputs of the shared trunk. So for each task specific, for each task, you compute a separate linear combination of the shared trunks, right? In the previous case, you had a shared trunk, and it was going into as input into the task specific parameters. In this case, a similar thing is happening, but now you have multiple trunks, and each task specific input to the task specific layers is a separate linear combination. So I think that was a bit confusing. So you look at your different shared trunks, and when computing what should go into the task specific layers, there is a separate there is a separate mechanism by which you combine these shared trunks for each task, right? So for example, just to take a random example, for example, this is your E1 layer, expert one, and this is your E2. So here you might want to compute zero point 0.5 E1 plus zero point 0.5 E2. And here you might want zero point 0.8 E1 plus zero point 0.2 E2. These are just constructed numbers, but this is the difference. Right. And yeah, so in the special case, you can choose that you want to keep the same weights for every task specific head, or you might learn separate linear combinations also. Okay, so this has been, again, this was a suggestion which came up in multitask learning. It resulted in some advantages. Let's see if a similar idea exists in federated learning. And indeed it does. So this is a paper from NeurIPS 2021. They wanted to solve this the personalization problem in federated learning. And they started with the following assumption. So they assumed that the data at every client comes from a mixture of M underlying distribution. So your entire data from across all the clients can belong to one of M distributions. It can be a mixture of these. And then every client samples some mixture of these M underlying distributions. So these are the ground truths, and every client is picking some samples from each of these, right? And then they proposed that they will learn personalized models where what they did first is they learn M shared models, and then every personalized model will be a linear combination of these shared models, right? So this is, as you can see, this is very similar to what we had in the multiple experts, mixture of experts case. So you learn M base models or M component models, which are shared across clients. And then every personalized model or every task specific model will be a combination of these. Right? And then every client, because it computes its own, because it computes its own weights, it gets a personalized model. And it turns out this indeed gives you some advantages. So they did experiments with a number of common data sets, and they compared a bunch of existing algorithms. So Fed average, Fed prox, clustered federated learning, and so on. And their method called Fed EM. So here EM stands for expectation maximization. This consistently outperformed all the existing tasks, all the existing methods across all the data sets. So there indeed was some value to computing these mixture of learning these mixture of base models, right? And again, we see the same thing that an idea from multitask learning was adapted to the federated setting. It can happen knowingly, it can happen unknowingly, but there is a lot of talking between happening between these two fields. Okay, let's look at one last architecture suggestion which people came up with. There's a question. How do these methods compare to other personalization models like clustering or interpolation in terms of performance? So, okay, so like whenever we talk about comparing the performance, because these are very high dimensional deep models, it becomes a subjective question. Like it depends on what kind of model you are using, what kind of algorithm we are using, what kind of tasks we are comparing. And as we can see here, for example, this FedEM proposal did better than clustered federated learning, right? But I'm sure there are subsequent papers on clustering in federated learning which have outperformed existing personalization methods. So these are very specific questions. And I would say that is sort of a beauty of research, that there are so many nuances you have to be careful about. So like you cannot make very general claims, but there are some rules of thumb you can use to get good enough performance, right? For example, the mixture of expert is expected to do absolutely better than the shared trunk architecture, because this is a more general architecture, right? So you can use some rules of thumb to improve your performance, but for like very different methods where neither of them is a generalization or special case of the other, it's very difficult to say ahead of time which will do. How Fed EM is different than Fed rep. Yeah, so it's the same difference as between this mixture of experts and the shared trunk architecture. So Fed rep was using the shared trunk architecture. Only the initial layers were shared, and then the final classification heads were client specific. Here, you have a bunch of shared trunks, and then every client is computing its own mixture weights to combine these shared trunks. So it's more general than Federated. Yeah, these are all good questions. Okay, so let's look at one final architecture. Uh, yeah, so in this case, what actually I should show you the figure first before. Okay, maybe not. Yeah, so this is called a cross-stitch network where uh, we learn individual models for each task, but in addition, we also do something much more involved in the sense that at every layer, so the aggregation between tasks or the talking between tasks is not happening only at one stage, it is happening between every few layers. So the input to each layer is a linear combination of outputs of the previous layer from every task. So suppose this is your model for this is uh, like layer L for task A and task B. And this is L plus 1th layer for task A and task B. Then to compute this layer, you talk to your previous layer, of course, but you also talk to the previous layer of the other task. And similarly, to compute this, you talk to the previous layers of both the tasks, right? So therefore, this cross stitching of layers is happening all over the network. And then how you combine these. So what are the weights you will use? These can be like specific to different tasks. So for example, this alpha 1, alpha 2, and beta 1, beta 2. So alpha 1 can be same as beta 1, alpha 2 can be same as beta 2, or they can be different. So, right. So this is exactly the figure I had drawn on the previous slide. So you have one layer of task A and one layer of task B. And then when you go to the next layer, you take a combination. So for task A, you take a combination of its previous layer and the previous layer of the other task, and so on. So suppose, and we are assuming that the architectures are identical. So if both tasks have identical architecture, then this is something which is happening. These are these are the input. This is the input layer. So this is parameters of one layer, and then you mix them somehow and get the output layer, right? And of course, if you get rid of these diagonal terms, then you have independent network for the two tasks. So you have one network for task A and one network for task B, right? Yeah. So this is what the entire architecture looks like. So in the previous slide, we were looking at this much part of the figure. So we had input layers, output layers, and we had mixing between them. So this is the mixing which was happening in the previous slide. Here we have the entire architecture. So you have multiple layers, and there is mixing happening at multiple stages here, here, and so on, right? So this is called the cross-stitch architecture because we have two independent networks, but rather than aggregating them only once, we are stitching several layers together, right? So off the top of my head, I don't know an parallel of this idea in the federated setting, but I would encourage you, if you are interested, you can explore if this idea has been proposed in the literature. Uh, I think there are some parallels between this cross-stitch idea and things like split learning or independent subnetwork training, where you train. So in both these ideas, you you instead of training the entire network at a single client, you train few layers at one client, the next few layers at a separate client, and so on. So you split your model across clients, and because you are splitting, so uh, it's possible that parallels to this idea might exist there or might make sense. Like this might be a new idea in itself if it doesn't already exist. So if someone is interested for uh, like a project idea to explore, then this might be something worth thinking about. Okay, so this was all the discussion we wanted to do about like architectures for multitask learning. So, as we discussed earlier, we want to balance how much information is shared between tasks. We first discussed the shared trunk model, where we had a shared feature extractor, which was shared between tasks. And then we had individual task specific heads. And this is fairly common in computer vision. And we also discussed a very similar idea existing in federated learning, where the clients are interpreted as tasks. Next, we discussed a more general architecture called multi-gate mixture of experts. Here, you have multiple shared trunks, and then you compute task-specific linear combinations which feed into the task heads. And again, we discussed an existing idea in federated learning where a similar thing has been explored. Finally, we discussed the cross-stitch network where the combination is happening at several layers. So we have task specific models, but then they are mixed layer wise instead of the mixing happening only once. Okay, so I'll wait 1 minute for any questions you might have. So next we'll discuss something called soft parameter sharing, where instead of coding in the architecture that how like different tasks have different parameters, we do it in a more subtle manner through loss functions. But I'll wait a few more seconds before we begin. Okay, let's continue. So this section will have a bit more math. In the previous section, we just looked at architectures and it was all hand wavy. Here, maybe we can say like things a bit more concretely. So we are going to talk about soft parameter sharing, where like we regularize the model parameters for different tasks, and we do that by penalizing the distance between model parameters. So we have models for different tasks, and because we want to make sure that there is some shared structure between these models, we will sort of enforce these different models to be close to each other. So we'll penalize the distance between them. And this is one idea, but there are more general methods to achieve something similar. So we can aggregate the different task specific losses in different ways to achieve different kind of outcomes. And then there is something even more general, which is multi-objective optimization. So instead of aggregating the task specific losses, we consider all the losses separately. And this is a like this is a huge area in itself, and we'll explore it in the next section. But in this section, we'll explore these things. Okay, so let's first, because uh, So mathematically, this idea of aggregating the task-specific losses is simpler. So let's discuss them first, and then we'll go to regularization. So one way is loss weights. So Li is the loss for the ith task, and we might choose to create an aggregate of the different task losses in a specific way. So at time t, we can assign some dynamic weight to lambda it to the task I, right? And this might depend on how quickly the model is learning this task, right? So that is one possibility. Why this might make sense? So imagine the following. If you have one task over which your model is making very quick progress, and you have another task on which your model is really struggling, in that case, you should not assign equal weight to both the tasks. You should focus more on the task on which the model is struggling, right? So this is what happens here. So just to make things more concrete, we can measure the progress of learning or the speed of learning by this ratio. So what is the loss value at the current time instant, and what was the loss value at the previous time instant? This ratio can give us an estimate of how quickly learning is happening. So if LIT is much smaller than LIT minus 1, then RIT is much smaller than 1, and we have very quick learning. On the other hand, if LIT is almost similar to LIT minus 1, then RI is very close to 1. In general, we expect some learning to happen. So, like, we should not consistently get this ratio larger than 1. If that is happening, there's something horribly wrong, right? But in general, this should be like close to 1 or smaller than. And then what we do is we take the softmax of all these RITs. So here T is the something called the temperature. And let me simplify this significantly. So suppose there are only two tasks. You have R1 and R2, and R1 is much smaller than R2, right? So for task one, learning is happening very quickly. In that case, what you would want is you would want lambda 1 to be much smaller than lambda 2, right? And this is exactly what would happen, because when you exponentiate something, it blows up, right? So if R1 is much smaller than R2, then e to the R1 is going to be even smaller in scale than e to the R2, right? So you will assign a lot more weight to task 2 than to task 1, and which is precisely what is happening here. So you want to assign higher weight to tasks at for which learning is much slower. Okay. And this has some benefits. So this is a table from a paper which studied different strategies of weighing things. And this DWA is what we just discussed. On the other hand, this equal weighing is where lambda 1 equal to lambda 2 always, right? And as you can see, there is some difference in error. So this is quite small, but there is some difference in error. So this makes sense in cases where there is very different learning speeds for the different tasks. Another related idea. So let me first describe it, and then we can discuss how these are related. So what you can do is you can decide that in which iteration the model will work with which task, right? So this is scheduling, that we can optimize or we can cleverly choose which task or which set of tasks to train at each training step. And this also leads to some performance gains. And again, this probability of scheduling a task, this should depend on how well your model is doing on different tasks. So one suggestion is that the probability with which we sample task I at a specific iteration is that, suppose we have some target performance in mind. So we have some target performance BI in mind, which we want to achieve. And the model with task I is currently at some level AI, right? Then this probability should be 1 minus AI by BI. If AI and BI is very similar, so we have almost achieved our desired performance. So we don't really need to work with this task a lot. If AI is much smaller than BI, then this probability will be closer to 1. And we want to work with this task a lot more, right? So again, high sampling probability for slow learning tasks. And therefore, there is very close connection between task scheduling and loss weighing, which we just discussed. And in fact, loss weighing is called implicit task scheduling because it also has a very similar effect. If the weights are very similar, there is a uniform probability of sampling different tasks. If the weights are very different, some tasks are more likely to be sampled than the others. Also, an interesting thing is whether we do loss weighing or we do task scheduling depends on which domain we are working in. So, for example, computer vision folks often do loss weighing, while NLP folks often do task scheduling. And in one of the previous lectures, you have seen an idea which is very similar to task scheduling. So, this was the power of choice paper you might have discussed a few lectures back. So suppose our original loss, here we have gone to the federated learning setting. So these are client specific losses rather than task specific losses. And this is our original loss. And what happens in power of choice method is that we select a subset of clients which have the highest local loss, right? So we are prioritizing clients which have higher loss or which are struggling to learn compared to tasks which are doing well, right? So this is very similar. This is exactly the task scheduling idea. And I think you must have seen this figure also. Like, what is the difference between like how it's more fair or it's more efficient than when clients are sampled randomly, right? So it makes faster progress. Okay, so these were two ideas in which we discussed how we combine the different losses. So task scheduling and loss weighing. Let's look at something slightly more involved. So we'll build this up very slowly. And this is the regularization idea. So as we discussed earlier, in regularization, we want to make sure that the models for different tasks are close to each other, right? We want to regularize that distance between different models. So what is the simplest distance? It's the Euclidean distance. And that was indeed the simplest idea people came up with. So we bound the L2 distance between task models. So what we do is for task I, we try to minimize the loss for that task, but we also want to make sure that this new model is closer to some global model, right? Or it might happen that the share, yeah, so XT is some global model, and we are building our local model on top of this global model. So we want to make sure that our local model XI is closer to this global model, right? And this was explored in the context of language processing in this paper from a few years back. And as I said, because we are enforcing that the models are closer to this global model, the task models are closer to this global model uh, from time t. It can be an average, right? It can be some like it can be a simple average. It can be something clever than that, but yeah. So yeah, so we are encouraging model parameters across tasks to be similar. And this was applied for dependency parsing in multiple language. And in this paper, they learned multiple models, one for each language, and they enforced all these models to be somewhat similar to each other. And this really helps if you have a lot less data. So if you have very little data, then it makes sense to have a global model or an average model or an aggregate model. And then for each specific tasks where there is very little data, you stay close to whatever your aggregate is. Again, because it's such a simple idea, it has been explored in federated learning, of course. So suppose you have one global model at the server, XT, and then what each client does is it minimizes its local loss, but it tries to stay close to the global model, right? And this happens at every client. So it's a very simple idea. This algorithm is called FedProx, and it is quite well cited. So the authors were from CMU. It's a it's a simple, elegant idea which worked really well. And there are some benefits of adding this proximal term in the federated setting. So as we just discussed, it ensures that the local updates stay close to the global model. In addition, the authors realized that this helps you incorporate, so different clients might, because of their computational capabilities, might do different amount of computation, right, in a given period of time. This prox term helped us incorporate uh, various amounts of computation at the different devices. And it also helped them handle data and system heterogeneity. So system heterogeneity is when different clients have different computational capabilities and so on. Data heterogeneity is when the data distribution across clients looks very different. And it worked well in a number of settings. So they compared Fed average with FedProx without regularization and FedProx with regularization. And as you can see, the blue curve for FedProx with regularization consistently does better than Fed average. Okay, so this was a very simple regularization idea. Let's build on top of this. So what about the following? Rather than enforcing the models to be close to each other, we try to find out some algebraic structure or some geometric structure between the different models, right? And one idea is that if different models share some low rank structure, right, and we can enforce this low rank structure in a number of ways. First, let's discuss how do we enforce it using subspaces. So when we impose low rank structure, essentially what we are saying is that the models have to share some linear dependence, right? So this is how this low rank structure is enforced. Each task specific model, it lies in some low rank subspace. So so theta is an H cross D matrix where D is the model dimension of the model Wi. So this belongs to RD. And H is typically much smaller than D. So theta will sort of act as a projection matrix where it projects into a low dimensional space. Right. So we have some offset. So this is an offset. And then this is some low dimensional term. Right. And then we can learn in the following way. So this is some aggregate loss where you have aggregated the different task losses. And we enforce some kind of regularization. So we want to make sure that the U and W are not too big. So this is some standard regularization. We impose a constraint that W has to satisfy this structure. So this is directly coming from here. We have just written it in a matrix form, like accumulating all the different task specific models. And because this theta lies in low dimension, because it is a low dimensional projection matrix, so we want to make sure there is nothing redundant in this theta. Otherwise, we can take linear combination of columns and like get a new column, right? So we want to make sure that whatever H columns it has, they are already linearly independent. So uh, like this is just for simplicity. But essentially, what we are doing is we are imposing this low rank structure on our model. There is another way we can impose a low rank structure, and that is using something called a trace norm. And the trace norm is the following. So uh, basically, we have an aggregated loss. So this would be some, oops, I should use lambda. So lambda LIWI. So we have some aggregate loss. We have some regularizer using the trace norm. And the trace norm essentially looks at the matrix W, where you have collected all the individual models WIs. You stack them vector wise or column wise in a matrix. You compute the singular values of this matrix and sum them, right? So essentially, you sum the non-zero singular values of the model parameter matrix, and this is what the trace norm is, right? And why does it make sense? So how are we getting low rank structure out of this weird looking regularizer? So the explanation is quite simple. Uh, you might be aware that when we have vectors, so suppose we have some vector lying in d-dimensional space, we can compute different kind of norms on it. So L0 norm essentially gives you how many non-zero entries exist in this vector x, right? So L0 norm is the number of non-zero entries in x. Therefore, it's exactly gives you the sparsity of the vector x, right? The number of non-zero entries of x is the sparsity of x. So L0 norm gives us that. On the other hand, L1 norm, it gives us the summation of absolute values of different entries of the vector x, right? So L0 norm gives number of non-zero entries. L1 norm gives summation of absolute values of different entries. It turns out that L1 norm is a convex relaxation of the L0 norm. And the advantage of being a convex relaxation is you can do some theory. The computation is much simpler. Also, it is a good enough approximation. So like the relaxation, it's an approximation, but it is convex. So it is computationally good. It is theory wise good, and it works well in practice. Now, let's move on to matrices. So L0 norm, L1 norm, we were talking about vectors. Let's move on to matrices. If we look at the diagonal, so if we look at a matrix T, which has different singular values of the matrix W at its diagonal, right? Now, suppose we look at the mm, yeah, so because it is a diagonal matrix, I can also write it in a vector form where different entries of the vector are the diagonal entries. So I converted this matrix into a vector, right? Because now I have a vector, I can also look at the L0 norm of this vector. So this will give me how many of the diagonal entries are zero, or how many of the singular values are zero and non-zero. It turns out this L0 norm is exactly the rank of the matrix, right? Rank of the matrix is, so rank is number of singular values, number of non-zero singular values, which is precisely what this L0 norm is giving us. So which is precisely what I've written here, that this L0 norm, because it is the rank, so it induces a low rank of the matrix. And just as we relaxed L0 norm of a vector to L1 norm of a vector and got a convex relaxation, similarly, we can relax this L0 norm into a convex relaxation, which is L star, which is exactly this trace norm. So trace norm is convex relaxation of rank of a matrix, right? Therefore, using this trace norm regularization, we can impose a low rank structure. So one way to impose low rank was using subspace. The other was using trace norm regularization. And again, there are advantages of doing this, imposing low rank structure. It gives you a lot of shared information across tasks. And this has been explored in this paper. So interestingly, this is just a 3-page paper. Like the fourth page is references. It was in some workshop in ICLR 2017, but it's quite well cited. So it was an influential idea. The first column here is single task learning, where you learn all the tasks separately. And the remaining 3 columns are where you impose this low rank structure. So there are different ways in which they impose this low rank structure, and all of them give some performance gain and like give better loss compared to single task learning. Okay. Finally, there is some very influential work in the domain of LLMs, which uses this low rank idea. So there is a paper from ICLR 2022. It is called Low Rank Adaptation, or LoRa for short. And this paper is so the last I checked a few days back, this had over 7,500 citations. So it's a very influential idea. I think it came from Microsoft research. And the idea is the following. The authors wanted to fine tune a GPT-3 model, but it had 175 billion parameters, right? So you have some pre-trained model, which is 175 billion parameters, and you want to fine tune it. This is a huge task. This requires a lot of computation, right? So they came up with something very clever. The entire transformer architecture they had, they at every block they split it into 2 components. So W is their pre-trained weights, which they already have, and then they assumed that whatever changes that happen during fine tuning have some low rank structure. So as you can see, these A block has a wide bottom and a narrow top. So in matrix formation, A is a D cross R matrix, where R is much smaller than D, much smaller than D. So it's a low rank matrix. Similarly, again, the same thing with B. Uh, it has a very small rank. And it turns out this worked really well. This saved a lot of computations. So this reduced the number of trainable parameters by 10,000 times. So from 175 billion, they were able to reduce 10,000 times. Like this is 0.01% computation. And this is what I just said. This is the pre-train weights. And this is the modification which you do while fine tuning. And since it was proposed, there have been several federated variants, so LoRa was on a single machine, several federated variants because uh, currently people are trying to like democratize LLMs, like move them onto the machines so that individual users can use them. So several federated variants have been tried, something called sparse LoRa or SLoRa, something called FFA LoRa or SA Fed LoRa or heterogeneous LoRa. Het LoRa was actually a paper by Yeji in, I think, some workshop in the previous NeurIPS. So yeah, several ideas have come up subsequently. Uh, I'm considering skipping this because this might take time and we have one more section to go through. Okay, let's discuss this. This is a cool idea. So far we discussed L2 norm regularization. You force different models to be close to each other. Low rank regularization, you force the models to have some shared linear structure. There is another idea so this was proposed long back. This is prehistoric in terms of ML research, but it's a very interesting and elegant idea. So I want to discuss it. So suppose we have K tasks as earlier, and we want to learn some small set of features. So for task T, we want to learn what are some features. And Yeah, so we want to learn the model for each task, and phi I are the features we are working with. So we have several features, but because we are doing multitask learning, we want to make sure that there is some shared structure across different models for different tasks. So we assume that even though we have several features, but every task only uses some of them. So there is a small set of features which every task uses, and the remaining features are useless, right? So this is what we want, what we imagine, and what we want to do. So let's consider the simplest case where these features are linear functions. You just take an inner product of some vector with the input x, right? And like this expression can be precisely written in this form. Here, U is going to be an orthogonal matrix. So because all the tasks are sharing a small set of features, if you look at these entries AITs, which are which denote how much weight different features get, in that case, if you collect all these AITs into a matrix, right, where the I's become the rows, so I's become the rows and T's become the columns. So T are the task and I's are the different feature functions. So phi I's, right? So you have D cross K. Now, if all the tasks share only a small set of features, then in this matrix, a lot of rows are going to be zero, meaning there will be many I's for which AIT will be zero for all T, right? Does that make sense? So when you collect these entries in a matrix A, it will have many all zero rows. This is what we imagine. But the question is, we don't know what n is. How do we find what is the number of features which are shared? So these guys came up with a clever idea, again using regularization. So you minimize whatever error you have across tasks. So here k is number of tasks, and for each task you have m samples, right? So this gives you, the first term gives you the error across different tasks, and the second term has some regularization which is strange looking. So this is a square, but you have two subscripts, 2 comma 1. What does this mean? Okay, so the first term is simple enough. Like we'll choose some convex error or some simple non-convex error, for example Euclidean distance. But for the second term, it is something really cool. So if we look at what are the entries of this matrix feature wise, so recall we collected all the entries in this D cross K matrix and we called it A, and these were AITs. If we collect the different rows of this matrix, so keeping I fixed, if we vary over the different tasks, so this will give us what is the importance of feature I over all the tasks. So feature I, importance of feature I over task. What this weird looking norm A21 gives us is you sum over D, so you sum over features, the L2 norm of every row. So you look at all the uh, importance coefficients of every feature over all the tasks, take an L2 norm, and then sum it over all the features, right? So you have a sum over features. So you have a sum over features, and this is an L2 now, where, yeah, I think yeah, let me know if this is not clear. So because you have a sum here and you have a positive quantity here, we can interpret this entire thing as an L1 norm of the row wise L2 norms, right? So that's why we have two subscripts here. So the first one, the 2, is about we are looking at every row and computing its L2 norm. And the 1 is we are taking the L1 norm of those L2 norms, right? And again, sparsity is back. Uh, And because we have an L1 norm, so it encourages sparsity of this huge d-dimensional vector of L2 norms. And therefore, this norm encourages that only a few rows will have non-zero entries because we have this. So we have a vector with several L2 norms, and we are taking its L1 norm, right? So this will ensure that multiple of these entries are exactly zero. And because every entry is a norm, it can be exactly zero only if that entire row is zero, right? So that's what we get. This A21 norm enforces or encourages only a few rows to have non-zero entries. And that's how we'll get that n, the number of non-zero rows. So it will depend on this parameter lambda and a number of things, but that's how we don't need to explicitly know what that n has to be. Okay, so just to summarize this optimization framework of multitask learning, first, we discussed task weighing or scheduling, where we were assigning a higher weight or a higher sampling probability to tasks on which the learning progress was slow. So there's a question, why we add this regularization term? Do we want to reduce the number of shared features? Yes, so that was exactly why we did it. So if you recall, we have D features in total, but we want to make sure that only N of them determine all the task models. So all the task models have to come from only N of those features, right? So these N features will be the shared structure between the task models. Why reduce the number of features? So, for example, your D can be very large, right? So, like you might, for example, in some tasks, you don't know what are good features for that task. In that case, you can collect a lot of information and you can design a lot of features, and not all of them are good, right? So, in that case, to find out what are the good features which are relevant to your task, you want to find out that subset which helps you get better performance. So rather than hand designing the features, you can collect a bunch of features and then through this regularization, impose this penalty, and this will choose your features for you. Make sense? Yeah. What is NAS? Sparse NAS. Sorry. What is NAS? Neural architecture search. I mean, yeah. So both these, that's why the names are so similar, like like hard parameter sharing and soft parameter sharing. Both are in some sense doing the same thing, but they are doing it in different ways. So the architecture search imposes this thing on like explicitly. Uh, Optimization does it in a more subtle manner. Yeah, so we discussed task queuing, task scheduling. Then we talked about regularization, several ideas in regularization, like simply we can bound the distance between task models, or we can impose some low rank structure, or we can uh, find a set of features which are shared. And one last thing, so this idea of shared set of features has also been explored in federated learning in this work. So the goal is for feature selection. So yeah, we are trying to, every model is based on a small set of shared features. Like in this specific, in the last regularization work, which I discussed. So every model, uh, because these tasks are related, they want to make sure that these different models depend only on a small subset of features. Okay, so maybe we should take a few minutes break now, like before we move to the last section. So let's take a 2 or 3 minutes break, and yeah, we'll go over the last section in 2 or 3 minutes. Okay, maybe we can get started. Uh, can you still hear me? If someone can respond in the chat.
Yes, we can hear you.
Okay, good. Okay. Thank you, Frank. Okay, let's go over the final section. I have less time than I intended to, but let's see. Okay, so now we are again looking at optimization, but a more general framework. So now instead of earlier, every time we had some loss, we were aggregating the different losses in some way, right? Now we want to minimize all of them at the same time. We won't aggregate anymore, right? So rather than minimizing a scalar function, now we are minimizing a vector function. And why does this make sense? So it turns out that when we minimize a weighted sum of task losses, it can result in a small subset of tasks being severely under optimized. So consistently, you do worse on a small subset of tasks. And this is clearly a problem. Another challenge is that when we have this kind of an aggregation, how do we choose what these lambdas are? How do we decide what weight to assign to different task class? And this is like a judgment call we have to make, and we don't always have enough information to choose these weights. And finally, uh, there are several possible sets of solutions we can come up with to solve this problem, right? On the other hand, when we minimize a scalar loss, the set of solutions we get is much smaller. So with scalar losses, we get the possibility of solutions or the possibility of models we can have is much smaller. So therefore, for the rest of this talk, we'll work with this vector of losses. So this is a multi-objective optimization formulation of multitask learning, and it was explored for the first time in this NeurIPS 18 paper. It's a really nice paper. I encourage you to look at it. So because now we don't have a scalar loss, we have a vector of losses. So it might happen that we cannot simultaneously do well on all the tasks. Like improving on one task might mean doing worse on another task. So this trade-off between tasks is captured by something called Pareto optimality. So Pareto was, I think, an Italian economist and engineer, and like expectedly in economics, he figured out that there are several trade-offs involved. So this Pareto optimality is named after him. So first, let's define what it means by for some x to dominate another solution x bar. It means that for all the tasks, x, the loss at x is not worse than the loss at x bar. So LTX is less than equal to LTX bar. Also, the vector of losses are not the same. So this means that there would be at least one loss at which LTX would be strictly less than LTX bar, right? So this means that X dominates X bar. X is strictly better than X bar. And a solution is called Pareto optimal if there is no solution X, no other solution that dominates X star. So if this condition is satisfied by some X star, it is Pareto optimal, and you can have infinitely many Pareto optimal solutions, right? So just to give a concrete example, suppose you have L1, the first loss at the L1 axis and the second loss at the L2 axis, and you plot the different loss values achieved by a model over these like between different trade-offs achieved. Suppose you get a figure like this, right? Now, at this point, let's compare these 2 points. So this is x2 and this is x1. At x1, L2 is better. At x1, L2 is better, right? But at x2, L1 is better. So therefore, if we had to choose between one of them, this doesn't give us a clear decision, right? So both of these points lie on, they are Pareto optimal. And therefore, at Pareto optimal points, you cannot reduce one loss without also increasing some other loss. So we really have a trade-off across losses at Pareto optimal points. And an interesting consequence is that if we are not at the Pareto optimal point, then we can we can reduce all the tasks simultaneously. So we can find a descent direction which will reduce all the tasks simultaneously. So this is a good check of Pareto optimality. If you are at a point from where you can reduce all the losses simultaneously, it's not a Pareto optimal solution. Now, because we often deal with non-convex functions, instead of Pareto optimality, we have to settle with something weaker, which is Pareto stationarity. So Pareto stationarity means that at such a point, at a Pareto stationary point, we can find a convex combination of our gradients for different losses, and this convex combination would be zero. So WIs are the different convex combination parameters. They are all non-negative. They sum to 1. That's how we know that they are convex combination coefficients. And there exists some convex combination of the loss gradients such that this convex combination is 0. Right. So this is the definition of Pareto stationarity. Every Pareto optimal point is Pareto stationary. Right. And as you can imagine that Pareto optimality is a stronger condition. When you go from optimality to stationarity, there is usually like implication one way. And because every Pareto stationary point, so at every Pareto stationary point, the following holds. either you get this condition. If it's not Pareto stationary, then we can find descent directions to simultaneously reduce all the losses. So either you are at a Pareto stationary point, or you can simultaneously reduce all the losses, right? So again, this is a good check for Pareto stationarity. Can you simultaneously reduce all the losses? If not, then you might be at a Pareto stationary point. So what we mean by simultaneously reducing all the losses, this means that if I have a vector D, I take its inner product with all the loss gradients. If all these inner products are non-negative, if all these inner products with the loss gradients are non-negative, that means minus of D is a descent direction, because the inner product with minus of D would all be non-positive, right? So this is essentially how you find a Pareto stationary point. And the first algorithm to use this insight was something called MGDA, multiple gradient descent ascent. And as we discussed earlier, descent direction. So as we discussed here, at a Pareto stationary point, this convex combination has to be zero. So like MGDA uses this result to find the descent direction, and the descent direction, it turns out, has to lie in a convex hull of the loss gradients. What I mean by convex hull is you look at all the possible convex combinations of all the loss gradients, and you construct a set of all such vectors. That's the convex hull. So the MGDA algorithm solves the following problem. It is it tries to minimize this norm such that the coefficients are all convex, right? So this is the MGDA algorithm. It looks at a convex combination of the loss gradients. It looks at its norm, and then it tries to minimize this norm over this convex set. This is the simplex. This is the probability simplex, because all entries are non-negative and all of them have to sum to one. So it turns out either this is zero, or whatever the solution, let's call it W star, whatever the solution of this problem, it will give you some coefficients such that you compute this convex combination and it will improve all the tasks. So it will give you a descent direction. So the same consequence of Pareto stationarity holds here, that either this thing is zero, which means you are at a Pareto stationary point, or you can find a direction in which you can minimize all the functions simultaneously. And MGTA has been used for multitask learning extensively. So, like one of the initial papers used it for this multi-MNIST data set. So what you do is you take two digits and you place one of them in the top left corner and the other in the bottom right corner. So these two digits give you two tasks, right? Left and right task. And left task is classifying the digit on top left. Right task is classifying the image on the bottom right. And it turns out that MGDA improves the performance significantly. So in this figure, these yellow lines show what is the performance you can achieve when you train separate models for the left and right tasks, right? So this is sort of the limit of performance you can achieve. Then grid search all these stars, they try to find a combination. So they try to minimize such a loss function where you minimize an average of the two losses, and they do a grid search over these lambda 1 and lambda 2. So depending on the lambda 1 lambda 2 values, you get these different stars. Uniform scaling is where lambda 1 and lambda 2 are both half. And as you can see, this MGDA does significantly better, and it actually achieves the best achievable performance if you do independent training for both the tasks, right? So it is doing significantly better than all the existing methods. And it has been used in other domains also, like multi-label classification. So there is a celeb A data set which has every image has 40 attributes, and these attributes are whether the image has person has eyeglasses, whether they have bangs, and so on. So for every corresponding to every attribute, you get a binary classification problem. And so you have a 40-way multitask learning problem. And they compared MGDA. So green one is MGDA. They compared it with a bunch of methods. And as you can see, so this is a radial plot. And these are the different tasks. So the closer you are to the origin, the better you are. And as you can see, the green lines are the closest to the origin, right? So MGDA is doing better here also. So like we discussed what MGDA does, but let's try to understand it a bit more. Recall that at a non-Pareto stationary point, we can always find a descent direction which simultaneously reduces all the losses. Right. This is what the claim was, that if you are not at a Pareto stationary point, you can simultaneously reduce all the losses with some direction. Right. So suppose we have such a direction and dt is that direction. So we update our model in this way. Right. Here, eta is our step size. So we go from xt to xt plus 1 using the direction dt. Let's look at how much the loss for each task changes. So going from xt to xt plus 1, the loss will change slightly. If the learning rate is small, then we can use the first order Taylor expansion. So Taylor expansion. And we get this right hand side. So this approximation is coming from Taylor expansion. And if all the tasks are improved, then this quantity would be less than 0 for all the tasks, right? This is essentially a consequence of the point being non-stationary, non-Pareto stationary. Right? So far, so good. Okay. Now, let's I'll describe something which would seem slightly different, but I'll connect the two in a short while. So keep this in mind that this is what you get at a non-Pareto stationary point. Now let's evaluate what is the task for which the loss changes the least, right? So this is the difference. This is the change in the loss at the ith task. We find what is the minimum of these. I think 1 over eta missing after the approximation notation. Uh, you mean here? Uh, so you have 1 over eta, but you also have an eta here. So that's why the two will get cancelled. Does that make sense? Yeah. Okay, so I think I have a little over 5 minutes, so I'll try to just finish this and then rush over the rest. Yeah, so this quantity is the minimum descent across all the tasks. This is how much the loss decreases between two consecutive updates, and we look at the minimum across tasks, right? So we get this quantity. And this, like, we want to make sure that this quantity is big. So whichever task has the least amount of descent, we want to make sure even for that the descent is large, right? But one way to do this is that I scale up d. I choose some a million times d. So I change d to this, and then this quantity would be large, right? So therefore, to avoid this kind of dishonesty, we also add a regularization here, right? So that we are kept honest. So now this is the minimum descent across different losses, and we add a regularization. And MGDA tries to maximize this minimum descent, right? So MGDA would try to find a direction which maximizes this. So we have two sets of observations. First, we had the idea that MGDA tries to find a Pareto stationary point, and now I'm saying that MGDA maximizes this minimum descent. Yeah. So I'm saying that MGDA maximizes this minimum descent. It finds a D which will maximize this quantity. But earlier I had said that MGDA is solving this problem, right? Earlier I had said that you compute this norm square and minimize it over the probability simplex, and that's what MGDA gives. These two look like different things. The only thing common I see is that you have gradient with respect to the task losses in both, right? So what is happening? So because I'm running out of time, I had one slide to discuss this proof, but I won't discuss it. I'll try to create a homework problem out of it. It's a relatively simple proof. It requires just one knowledge of one fact about optimization theory, which I'll give as a hint. So, okay. So it turns out that these two things, trying to maximize the minimum descent and solving this problem, they are the same. Okay, so MGDA maximizes the minimum descent. So it sort of tries to make sure that all the task losses are reduced by the same amount, right? If you are trying to maximize this some, if you have multiple quantities and you are trying to make sure that the smallest of them is also large, you're sort of equalizing all of them, right? So it seeks equal descent across all task losses. Uh, but what if some task has a very small loss scale? So suppose I have two losses which are of the same scale, but then I multiply one of them by a very small constant. In that case, how will you make sure that there is equal descent across all the task losses? So this is a challenge of MGDA, which a subsequent work fixed. And how it fixed was, rather than looking at this absolute difference, it looked at the relative difference. So this is quite recent work from URIPS last year. I'll skip a lot of things here because yeah, just in the interest of time. I would encourage you to look at these and contact me if you have any questions. But I also have to skip the federated part, uh, which I don't like. Okay, so essentially, we in this section we discussed the multi-objective optimization formulation of multitask learning. And we discussed that if a point is not Pareto stationary, you can simultaneously reduce all the task losses. And we discussed first the MGD algorithm, but there are subsequent more advanced ideas like FAMO, PCGRAD, or uh, projected conflicting gradient algorithm. There is something called CA-GRAD, the conflict avoiding gradient, and so on. Okay, so in the last minute, I want to mention some open questions, which if some of you is interested in. So first is in all the multi-objective optimization section, the last section, which I mentioned, uh, the solution would be some point, some Pareto stationary point, right? But you don't have any control over what kind of point you will end up with. You have an entire Pareto front, or you have an infinite set of Pareto points, but you cannot control which point you get. So, like, how do we make sure that our solution satisfies certain preferences across tasks? This is like a very active direction. And Barish, one of your TAs, was led a work which did something similar recently. I was also involved in this work. Second, whenever we do ML, we want some kind of generalization guarantees. It turns out for multitask learning, there are a lot of not understood questions. And finally, the impact of optimization on multitask learning is also not very well understood. I would encourage you to look at this very recent paper. Uh, yeah, these are the references for the lecture. Thank you so much for listening. And yeah, see you in the next class.